If a function is both one-to-one and onto, it's called a one-to-one correspondence, or bijection. Let's do an example. Let f from z to o be defined by f of n equals 2n plus 3. O is the set of all odd integers. Show that f is a one-to-one correspondence. Okay, first, let's show that f is one-to-one. So suppose f of n1 equals f of n2 for arbitrary n1 and n2 in Z. Okay, so then 2n1 plus 3 is 2n2 plus 3. This is by definition of f. Now subtract 3 from both sides. And divide out by 2. Okay, so we get that n1 equals n2. So f is 1-to-1. Next, let's show that f is onto. So let m in O be an arbitrary odd integer. Okay, we need to show that there is an integer n in Z such that f of n equals m. Okay, this is what we need. Now, since m is odd, m equals 2k plus 1 for some integer k. Okay, so it suffices to show that there is an integer n in Z such that f of n equals 2k plus 1. Okay, if such an n exists, then 2n plus 3 would be 2k plus 1. Now, solving for n, we get k minus 1. Okay, so let n sub 0 be k minus 1. Then n0 is an integer, since we have k is an integer and k minus 1 is also an integer. And f of n0 that's by definition this. But n naught is k minus 1. And simplifying, I get this 2k plus 1. Okay, but that's just m. Okay, so there exists an n in Z such that f of n equals m. Okay, so f is onto. And since f is both 1-to-1 and onto, f is a 1-to-1 correspondence. Okay, let's do another example. Okay, let B be the set of all finite strings of zeros and ones. So an example of such a string is 100111. Let f from B to B be the function that takes any string B in big B and sends it to the string obtained by replacing each 0 in B by 1 and each 1 in B by 0. For example, f of 100111 is 011000. So it just swaps the zeros and ones. Show that f is a 1-to-1 correspondence. Okay, so this function that swaps the zeros and ones is a 1-to-1 correspondence. We want to show that. Okay. First, let's show that f is 1-to-1. So suppose f of b1 is f of b2 for arbitrary strings b1 and b2. Okay, if we replace each 0 in the string f of b1 with a 1 and each 1 in f of b1 with a 0, the result will be the same if we did the same thing to f of b2, because f of b1 and f of b2 are the same string. Okay. However, swapping the zeros and ones in f of b1, that gives us back b1. Similarly, swapping the zeros and ones in f of b2 gives us back b2. So b1 equals b2. And therefore, f is 1-to-1. Okay, next, show that f is onto. Let S be in B. Let it be an arbitrary finite string of zeros and ones. Okay, we need to show that there is a string B in B such that f of B is S. Okay, so we need to find that string B. Okay, so let B0, let it be the string S with the zeros and ones swapped. Okay, so we took an arbitrary string S and then we swapped the zeros and ones in S. That's what B0 is. Okay, then f of B0 is S because swapping the zeros and ones twice returns the original string. Okay, so remember B0 is S with the zeros and ones swapped. And then we take f of B0, so it swaps the zeros and ones again, giving us S. Okay, so we just found a string B0 such that f of B0 is S. And so f is onto. And since f is 1-to-1 and onto, f is a 1-to-1 correspondence. If f from x to y is a 1-to-1 correspondence, then there is a function, f inverse, from y to x, which sends each element f of x in y back to x in big X. So here's a diagram. F sends x to f of x. F inverse, it just sends f of x back to x. Okay, this function is called the inverse function of f. Let's do an example. Let f from z to o, the set of all odd integers, be defined by f of n equals 2n plus 3. Find the inverse function of f. Okay, if m is in O, then m equals f of n for some n. In Z. So m equals 2n plus 3. Solving for n, let's subtract the 3 and divide out by 2. Okay, so f inverse of m is this. Okay, so here we picked m and o, and we said that m equals f of n for some n in z. Okay, and then we found that n equals n minus 3 over 2. So to get back to n, we would have to do this to m. That's why f inverse of m is m minus 3 over 2. Okay, so f inverse gets us back to n. Let's do another example. Let B be the set of all finite strings of zeros and ones. Let f from b to b be the function that takes any string b and swaps the zeros and ones. Find the inverse function of f. Since f of b is the string b with the zeros and ones swapped, to get back to b, we just need to swap the zeros and ones once more. So if s lies in b, then f inverse of s is f of s. In other words, swapping the zeros and ones in s. Okay, note that in this example, f inverse is the same as f.